This workflow building is part of a data mining and machine learning course at the Hochschule Ruhr-West in Mülheim an der Ruhr. Therefore, we already started previously with iris data. This is just a regular iris data set that you may find everywhere. It has been imported, and to make some interesting transformations, we decided to just calculate the sepal area, and the petal area here is done simply by calculating the petal length times the petal width. There could be more elaborate approaches to do so. This, however, was deemed sufficient for this particular course. We then normalized all parameters in between 0 and 1 so that they get an equal amount of share. So that was that. Now we wanted to apply the support vector machine algorithm, and there are in my particular installation two possibilities. We have the KNIME implementation, the SVM learner. We do need an application here as well, or we could use the one provided by WK. I'm only gonna do one example for now, so I will go with the KNIME implementation, and you see here the learner is directly attached to the preprocessed data. That should not be the case. We should partition the data first. Now, often you will find partitioning into 90 to 10, or you will find different types of partitioning where you get just a portion of the fixed portions of the data. I personally prefer a 70-30 separation. Because we don't have so much data, we cannot make it more than 70-30, but the more we can test, the better it is for us. We do stratified sampling at this point because we have 3 classes, otherwise the problem with the separation into classes of the data and having imbalances there in training or test data would be too great. So we use stratified sampling, and we do a relative draw of 70% for training. So the training data is on top. We can verify that by right-clicking the partitioning node and see here first partition, and the first partition is, of course we have to execute that to see. The first partition is about 105 rows, so the other partition would be like 45 rows exactly, and so this is then the smaller part that goes into our predictor. And now we have to set up the learner. Now the class column is the class column. We do not change any of the settings here for now, and we just say okay. Do we have to do anything here? No, we don't. So we can just go ahead and execute this. What we get out of that is a classification. As you see here, clearly only the test data has been classified. Now we want to understand something about how good our scoring, or how good our calculation was, or how good our model works, and so we can use the scorer, and there we have to change the first column to class, and then we have the prediction, and then we can execute that, and we see yes, that worked fairly well. We have 4 misclassified instances, and if you look at the accuracy statistics, they also look pretty nice. Now this result could be due to chance. So what we might want to do is take this out and put it into a loop. We might use this type of loop. There might be other loops we may want to use, and depending on how much data we have, we may want to change the number of iterations here. I personally use 10 iterations here, just to be sure that the result is not due to a split in the data, but that the result can be reproduced, and we always get a good result, or we don't. So then we need a loop end. and there are a number of loop ends. I will take one with 2 ports, and I feed the... So now that we connected the scorer to the loop end, and we have 10 iterations that we're gonna run, we just execute this and look at the collected results. What we see here is multiple rows, 3 rows per iteration. The iteration is written on the right, 0, 1, 2 and so on. 9 is the last one, and then we can see that the accuracy is typically above 0.9, and therefore we can say, okay, this was not just by chance, this was a good result that we could work with further. Let's try to summarize this result. As I just showed you, there were multiple rows per iteration, so we may want to just look at the accuracy results, and for that we can create a row filter, and we can go to accuracy and say only missing values match. That means we look at this row if there are missing values and then exclude those rows, and so now we will have excluded all those rows that do not have a proper accuracy value, and now we only have the 10 iterations as we intended. This is a bit more condensed, nice for us, so we can more easily work with that. So if we use a column filter as well, then we can get rid of the columns that we are not really using. We were only using the accuracy here, and that is enough. Whether the accuracy is enough for such a data mining project is a different question, but right now for us, for this particular task, this should be sufficient. So we look again at the data. Okay, we have now the accuracy. We may or may not need the result of the iteration. We probably at this point we don't need it, because I just want to know approximately the average, and to get the average we can just get the col mean, and this is of course of the accuracy column, and then we execute that, and what we get here is the new column, and we probably would want to rename that to average accuracy, and after doing that we will see that the average accuracy is, as we thought, above 0.9, so that is a good result. So now let's recall the SVM learner. The support vector machine learner has a number of fields that we could work with. Not only that, it has multiple kernels that we could work with. So depending on the kernel, depending on the settings of the kernel, we might get different results. That is important to note, and this is a data set dependent setting that we have to find here. So we have to optimize the settings here, and specifically choosing of the kernel for a particular data set. That is not very nice if we have to do that manually. So what I would suggest is we should try to optimize this automatically. For that we will use an optimization node. There it is, parameter optimization loop starts. So we have another loop that we're talking about. You see here the red dot, that's a variable port. So here we have to find the associated variable port in this other loop start. We have to do it outside of this loop start or inside of this loop start. But for me, for my understanding of this, I want to have a 10-fold cross-validation here in this inner loop, and then try a different parameter setting, so that a parameter setting, if we do it in here and then do a cross-validation loop outside, it wouldn't make any sense. So basically we have to do the parameter optimization outside here. Another thing we need is of course the loop end. If we would connect it here, that wouldn't work. So there's one more thing, we have to connect it outside, and we need the information of the quality of the prediction which comes out of the scorer and then was summarized here in the math formula. So that does not really go in there, as we can see. So what we need is a change to a variable, and yes, we have to connect it here. So what comes out here should be changed to a variable, and clearly we have to execute this here first before we can come there. So let's still connect this here. After this we should be done. So this should be giving us the result that we want. Here in the optimization node, it should give us as a result the best parameters given our input here. And this input is now the essential thing that we have to deal with. That is very important. Right now we have no parameters. But what are the parameters that we can optimize? Here we can look at the SVM learner, and the dialog cannot be opened. Yes. That's a bit odd. So as a workaround, we just open a new SVM learner, attach it somewhere to our data, and then open this to see what are our options. Right now we see that we have these three options: polynomial, hypertangent, RBF. So if we go to the flow variables that exist in here, then we have kernel param bias, we have kernel param power, and so on and so on. And these are the things that we should set up. Now we cannot keep this open and open our parameter optimization loop start to set up a parameter to optimize. So what we can do is just remember kernel param bias and then open up this to add a new parameter, and this new parameter should be kernel param bias. We could have a start at 0.0, we could end this at 1.0, and we can have a step size of 0.1. That seems appropriate. This means we would then change this particular parameter in 10 steps. So that means 10 steps for the parameter optimization here, and 10 cross-validation attempts in this loop. That means for this particular optimization we already have 100 rounds that we should calculate the support vector machine. We can use different optimization strategies, and here we can use, for instance, the Bayesian optimizer. That would be one option that we can choose, or we can just have the brute force and so on. There are many opportunities. You see, now we have the chance that we can delete this other SVM learner again, and we can access this particular one. So I just looked at the bias. Now we have power and gamma. What's their real name? Kernel param power and kernel param gamma. Those were the two things. Yes, kernel param power. Kernel param power and kernel gamma. So these are the three attributes that we want to optimize. They all seem to be ranging up to 1.0. No, it's not really true. We have to check out what the ranges are, and then we can put real values into our optimization here. So for now we could just say, okay, this goes up to 2, this goes also up to 2. That's a bit much. And yeah, we could optimize by 0.2 in this case, or that we're using Bayesian optimization, so we don't really give a step size here. Okay, this means we now selected 3 attributes: However, we did not really use those attributes to optimize the SVM learner here. In order to tell our SVM learner which numbers to use here for the power, the bias, the gamma, we go to the flow variables and then we go to kernel and we set it up to be using the bias. That's why we chose to use the same names, so that here in this particular setting up we have no particular problem. And now we connected the two things. I just clicked OK to save it. Now these, as you can see down here, these numbers are not the numbers that are written here, but they are controlled by a variable. This is apparently not showing it completely, but okay. So that means now the parameter optimization loop start uses 3 different attributes. These attributes are optimized over a number of folds, and within each of these optimization attempts we make a 10-fold cross-validation. Our cross-validation happens, where is there? Our cross-validation happens here. So we have 10-fold CV in here, and outside we have the parameter optimization. So we do have a few other things that we have to take care of at this point. We get out of the math formula some information like this average accuracy. Now we don't want to have many rows of this because we're really only interested in the average accuracy, so we can use a row filter to condense that information to just one row, and that is very simple process. We just say okay, let's use just the first row because it doesn't really make a difference which one we use, they're all the same information. So now we only have one row left. Here's our average accuracy, that's the thing we're interested in. Now we have one more problem. We have this row ID here, and this row ID is 3 at this moment. But when we have a different iteration, it will change. And then if we want to use it, we cannot see that, wait, I have to execute this. Now we have to choose for which variable we want to use the optimization, and this is at the moment in row 3. But that's of course a very bad limitation for us because row 3 is prone to change, so we cannot depend on row 3. So basically what we have to do is we have to, that's one option, we can insert a constant value column here, and we can just append that, and that should be our new row ID, and it is a number integer and we just call it 1. And now if we do this, if we execute that, we will now see that we have this RID here. This is not our row ID yet. We do have to use the row ID operator here, and now we can change this existing column RID to be our new row ID. So now if we execute that, we will see that our row ID is now 1. And so each time that we let this run, our row ID will be 1. And now we can depend on this row ID in our optimization node and choose 1 here. And maximized is what we want. This should be maximized because the better the accuracy, the average accuracy, the happier we are, and therefore this should be maximized. Now we are all ready to go. Support vector machine takes a bit of time even for this small data set, so that's why I executed this workflow, and we have now the results, and we have the results. We can look at the best parameters. This is what this particular workflow came up with as the best results for the 3 parameters that we wanted to optimize. Now keep in mind, we did not look at what are the cornerstones of these parameters. They might be 0 and 1, might be 0 and 2, there might be larger values. We see here for the kernel param power that a value larger than 1 was selected. So this is one thing we have to check out. First of all, what are the boundaries? Then the other thing we need to check out is we may want to use a hypertangent or RBF instead of this polynomial. So there are other opportunities. So this could be a thing that we would go into in the optimization. Regardless of what we do, we get the best parameters, and we can now use these best parameters to feed a new SVM learner and then train a new model, and this model we can use. Or alternatively, we could just save the model that the SVM learner learned and then use that model. There are a few complications in both approaches, but this is something for later on. Right now, we just wanted to know what is the optimal setting for this particular workflow. The other thing we can look at is all results, and here we see we did about 100 iterations, and in these 100 iterations we found a number of times a perfect solution, but typically the solution was above 0.9, and we have some attempts where the solution was very bad. That here, in particular down here, may be depending on the settings. If we do a larger study for this, we may really find some dependency on these settings, and when we do this, they were not sorted, so the results were in a random order, kind of. It's not that we did an optimization towards the correct result, we just did a random walk and picked the proper and picked the best result that we were able to find. So that concludes our optimization, and I will upload this to our KNIME hub and share with the link below the video.